Okay, so what we will do is we'll try to copy this particular file in another file and try to read this data in Octave. So obviously we only need numerical data, so we will delete all this text data, whatever is there before this numerical data, and let's see. So first thing that we need to record here is the sampling interval is given as 200 samples per second, and three component data that we know.
ठीक है, अभी कनेक्ट हो गया अपना टैब में ना, तो भी मैं बाकी इसमें देखते हैं यार इसको बाद में फिर, ठीक है। चलिए, ओके बाय।
X, Y, and Z. So let us try to do that. So trial three component data, that's our input file, and you can look at this. So we can have a look at it, how this looks like. GNUplot is a plotting software that is also available for free. You can download from this web page that you can see, gnuplot.info, and even Windows versions are available. So this is what this is what the data looks like. So as you can see, this is the background noise of the sensor pre-event record, and the actual event has started somewhere here. So we need to figure out what is the exact time, and similarly this was probably terminated much earlier. We should have had a similar kind of trace at the end, and the record actually continues up to that. The event earthquake vibrations continue up to that. So as you can see, the mean square value at this level is much smaller than the mean square value that we have here. So that is probably an indication that some vibration was still going on when we stopped recording, or when this record was truncated. Nevertheless, it's hardly of much consequence here as far as engineering applications goes. Not much intensity is left here, except for the theoretical issues that velocity of the ground at the end of the earthquake should vanish, should go to zero, which may not happen in this particular case, because the event has, the record has been truncated prematurely. So this is about 0.125 g peak ground acceleration that you can read from this trace directly. It's about 0.123, about 0.123 g. Yep. So, point, pardon? Yeah, 0.125 is, this is 0.1238, this particular peak. Right, so let us try to, and let's look at the other component. This syntax that you see here, 0, that denotes the just the index number, the number, data number, and data number multiplied by 0.005, that's the sampling rate. 0.005 seconds apart, this data has been preserved, recorded. So that gives us the timeline. Otherwise, we would have just seen the integer numbers here, the sequence number in the data series. And X, and second item here is the column, which column to plot. So first column is the X data. Now if I go to see the, okay, let it remain. Second column, so this becomes the second column, that is Y data, and the peak here is about 0.129 G, and here it is 0.125 G. So and then the third component, third column, this is the vertical component, and yeah, looks good. So we can also plot all of them. Let's say this is X, this is Y. Let us, if I want to overlay this, then I just say replot. So that goes with X and Y on the same plot, and then Z will also go on the same plot. I can also have multi-plot option. I can say set size, scale 1 and 0.33. So that's the y-axis will be scaled by 0.33, and x-axis will be scaled at it will be retained as same. So set multiplot, then set origin 0 0, plot again the same. So this is X component. Now I will shift the origin. Earlier the origin was kept at 0 0, so this plot came here. and now I will shift the origin to 0, x0 and y 0.33, because that is what the scaling is. So and then here plot number 2. So that goes.
Excuse me, sir.
Yes. Then just a minute.
Hello, excuse me, sir.
Yes, just a minute. Uh, so this is the 3 component plots that we. Yes, please. Any questions? So this is a simple, and this works. GNU plot can work as a using a script also. So this entire process can be automated. So that is quite handy. And in case if you have any other favorite plotting software, I mean that also you can use. But plotting is a very very important and useful tool for strong motion data processing. So we need to have some kind of plotting. Of course, Octave itself has a plotting system which is based on, which uses GNU plot actually. So internal plotting in Octave is based on GNU plot. So let us start.
Excuse me. Hello.
हाँ जी हाँ साहब.
हाँ सर नमस्कार.
Good
एक्चुअली
morning, good
सॉरी
morning.
मैं थोड़ा लेट हुआ. एक्चुअली देयर वाज सम इशू इन माय लैपटॉप.
जी जी वो पता चला मुझे.
जी जी. ये एक्चुअली बिकॉज आई मिस्ड अर्लियर पार्ट. So this GNU plot basically it is a separate software.
जी हाँ, GNU plot is a separate software. Again it is a free software. gnuplot.info से आप डाउनलोड कर सकते हैं.
Okay, okay.
And Octave का जो native plotting है, that is actually based on this software. It is integrated into Octave as well.
Okay.
तो लेकिन अगर आपको अलग से कोई सिर्फ प्लॉट ही करना है तो it is
Okay.
better to just use native plotting software.
So this GNU plot dot what you told?
Info, info.
Info. So this can be used for plotting any type, any other, any type.
It's a very
data.
versatile system. I'll just show you.
Okay.
So GNU plot homepage. So this is what it is, and these are the binaries जो आप डाउनलोड कर सकते हैं. करंट वर्जन इज 5.4 और डेवलपमेंट वर्जन 5.5 है. और इसका यूज़र मैनुअल इधर है, और गैलरी है, डेमो गैलरी कि क्या होता है, कैसे होता है, यानी क्या क्या कर सकते हैं. And download link is here, and you can actually get download from Windows version यहाँ से है, और
जी जी जी.
बाकी मैक ओएस का वर्जन यहाँ से मिलेगा. बाकी तो यानी सोर्स फोर्स पे तो सोर्स कोड वगैरह मिल ही जाएंगे.
अच्छा, ये जैसे GNU प्लॉट है, हम लोग एक सर्फर भी यूज करते हैं.
हाँ
तो,
हाँ हाँ.
व्हाट इज द डिफरेंस बिटवीन टू?
बस अलग अलग सॉफ्टवेयर हैं, दैट्स ऑल.
ओके, बट बोथ हैव ऑलमोस्ट सिमिलर फैसिलिटीज.
हाँ हाँ हाँ, यानी GNU प्लॉट इज एक्चुअली मोर वर्सेटाइल. आप इसमें कर्व फिटिंग भी कर सकते हैं. GNU प्लॉट हैज दिस रिग्रेशन इंजन बिल्ट इन.
Okay,
आप
okay.
बेस्ट फिट कर्व यानी आप फंक्शन देके यू कैन एक्चुअली डू अ लीस्ट स्क्वायर्स फिटिंग ऑन विद इन जेएनयू प्लॉट.
Hmm, 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 hmm. Okay. So, whatever functions we have in Surfer,
हाँ हाँ
similar we can have here also,
हाँ हाँ
and
हाँ
even
बिल्कुल.
the much better. You
Much
can
better
say.
and Surfer obviously it's a commercial software.
Yeah, it is a
So
commercial.
and
Yes, yes.
this is public domain. You can use it for I mean freely without and distribute it freely without any uh, payment
Okay, okay,
involved anywhere.
okay, okay. That's good.
So
So with your training, we are saving lot of money also.
uh,
Yeah, yeah.
जी हाँ
Because
यानी
actually, uh,
I do not use any proprietary software ever.
yeah. Okay,
तो
okay, okay.
यानी सिर्फ एक लैपटॉप में विंडोज़ ऑपरेटिंग सिस्टम है, बाकी तो मेरा ऑल माय वर्क इज़ ऑन
जी,
लिनक्स एंड
जी, जी, जी,
आई यूज़ ऑल पब्लिक डोमेन सॉफ्टवेयर्स
जी.
and I actually take it to the extreme. I do not contribute my articles to any journal which insists on receiving manuscripts in Word.
जी.
I prepare my articles in LaTeX and LaTeX से ही जो जर्नल LaTeX एक्सेप्ट करते हैं, I contribute articles only to that. So
ओके,
anyway,
ओके.
so आप
जी, जी,
JNU plot आप देखिए, आपको
जी.
you will find it very handy and very useful.
ओके, ओके. दैट्स गुड. या.
तो इसके लिए मेरे कुछ स्क्रिप्ट्स भी हैं जो कि यू फाइंड ऑफन ए ट्राइपार्टाइट प्लॉट जो हम कहते हैं फॉर पर्टिकुलरली फॉर प्लॉटिंग ऑफ रिस्पॉन्स स्पेक्ट्रा,
जी, जी,
जिसमें
जी.
वी गेट द displacement, pseudo velocity and pseudo acceleration on the same plot. There are actually 4 axes. So
जी.
that particular plot we already have, and I have that. I created a script to
ओके.
plot that kind of graph paper using GNU plot. So you can use that
जी,
and work on that. So
जी, जी, जी.
let me show you how that particular thing looks. So you can see this. So this is what it looks
जी.
like.
या, या.
Oh. So x-axis we have natural period, and
जी,
then y-axis we have pseudo velocity, and then
जी.
two inclined axes, one for pseudo acceleration and one for displacement. तो प्लॉट तो हम एक्स वाई प्लॉट वी गेट दिस नेचुरल पीरियड वर्सेस सूडो वेलोसिटी. ऑफ कोर्स दिस कैन बी इन टर्म्स ऑफ नेचुरल फ्रीक्वेंसी एज वेल, इंटरचेंजेबली. वो प्लॉट आई मीन वील हैव टू डिफाइन एक्सेस सेपरेटली एंड देन these axes will of course change, interchange, and then we just plot a simple xy plot, natural period versus pseudo velocity. But the values, once we plot that values, we can read from any of the axes because of mutual relationship between the spectral displacement, spectral velocity, pseudo spectral velocity and pseudo spectral acceleration. So we can read from different axes depending on the period. So if we are operating in the acceleration sensitive region, that is short period range, then we just read it off from the acceleration axis. If we are in the intermediate range, then we use this pseudo velocity axis. If we are in the long period range, which is displacement sensitive range, then we read off from the displacement axis. So that is how we do that, and we can have this particular, you can see this script. Uh, so this is the script that I had created using GNU plot, which can generate this grid line, this grid complete graph paper, and then at the end it will also plot this data graph plot. So at the end you have this graph paper, and then you have all the whatever data response spectra that you want to plot, and you can plot using this script. So this script is also available for download from my web page. So nevertheless. So let's go back to our are you able to see this Octave prompt?
Yeah.
Let me.
Sir, are we recording this session?
Yes, we are recording this. Let me just confirm. Yes, it's recording is on.
Okay, it was not visible, that's why.
So okay, let me this is actually Linux platform, so it primarily works on command line. I prefer to work on command line. Let me give you the usual feel that you will have on Windows platform. So you will have this kind of an interface. Okay, GNU new version is released, so fine. So you may also update the Octave. New version of Octave has been released. So of course Octave help is always available in this command, in this particular interface. So you can just search complete Octave manual is here, and you can always refer to it as you go along. So we also have this simple editor built into it where we can write the scripts and execute it subsequently, and this is of course the command line. So we can so present working directory is home. So let me just go. So now present working directory is NHPC, where the data is. So our data file, as you can see, trial 3 component trial data. So we will try to open this. So in order to read the file, we need to define a file handle which will be used for in the software to refer to this file. So we define this input file as fopen trial 3 comp dot data, and this has to be opened in read only mode. So I file is an identifier which defines this which now associates. So it's like if you are familiar with Fortran or any other programming language, so this is just the file association. We just indicate the unit number or assign a file handle file channel to map it to a particular file name that is there. Now we can read this using fscanf. So let's see. I can either let's say file handling, we can see here input and output, basic input and output, sample simple file IO, and this is C style input and output. So save and load command. So this is one simplest way to save the data to a file. So you can read the options. What are the different options? So what we are using right now is this C style opening and closing of file. So this is what we used. So instead of this variable, I just use the name of the file directly here. So this is file identifier, and using fopen, that's the file open command to associate this particular file with this identifier. And this is the mode, whether we want to open it in write mode or in read mode. And then whatever we need to do that, we can use this file identifier and continue. After we are done with the file, then we need to release this file identifier, association of this file identifier with this particular file, and close the file. Right. So this is what the basic structure is. And these are the default modes. R is the default, that is to open the file in a read mode. W is for writing, and append mode A is for writing at the end of the file. Whatever the contents are, it will go to the end of file and start writing there. And R plus is for reading and writing existing file. You can read, and then at the end you will write to that. W plus is also for reading and writing, but the previous contents will be discarded. And A plus is again create file for reading or writing at the end of the file. And then it is a text mode or binary mode. So which mode we need to open this, what kind of file we are trying to read, and so on. So mostly we'll be only dealing with ASCII file, so it will be the text mode, and that's the default. So then the input is, so these are the commands for getting the input. So this is line wise input, but we need to find out formatted input. Our data, as you can see, is 3-column data, that's a floating point data. So we use fscanf. So just like in C, So we will have this file identifier that we have just opened it, and then template and what is the size, and it's a function which we can not all the arguments are necessary. We can provide them whatever information is whatever information or whatever specification we can give for the data capture, and let's try to do that. Okay, where is Octave? Yeah. Okay, command window. So data we will save in, let's say, AX, AY, AZ. That's a file, and which will save read the file from iFile, and the template is and we can also say number of data points, total number of data. So this data, as you can see, AX, AY, AZ, it has actually computed, read everything in the single array. AX, AY, AZ. So these are the first three columns, first three data, and let us look at what this file had. If you see, these are the three data which are the first three, the first row that you see here, that is the first three data that we have, right? So obviously that is so in that case probably this is not required. I can just say only, okay, doesn't work. It's already at end of file. Okay. So what we will do is segregate this data into steps, into three different files, and we'll do that using for loop. So what is the syntax for a for loop? Okay, for loop in parallel for. Okay. So now we need to extract this, separate this file that we have ax, ay, az. Uh, so what we will do is we will write a for loop which will increment in the steps of increment of 3, so that once we have I is equal to 1, then the next I would be 4, so that 1, 2 and 3 can be assigned to different uh, different arrays. So that size will be n dot will be equal to n by 3, and that is 9840. That is the total number of samples that were there. If you look at the original file, so 9840, these are the number of samples. So total number of samples that we have is 9840 multiplied by 3 component data. So that is the amount of data that has been read, and we need to change it for. So we define ax as zeros of n dat 1, and if we use semicolon, that will suppress the output. Otherwise all information is it will keep on octave displays by default if we don't suppress the output. So we define 3 arrays ax, ay and az, which are 0 of the desired length n dat, and we just go for I is equal to 1 to n dat No, it is not working. No, I again goofed up. Sorry for this trial and error. No, it is fine, and that is fine. Yeah, I got it. Okay, so this is fine. So we can also define time is equal to 1 to lean space. Okay, let us find out what is lean space. So this is linearly spaced data uh, starting from start value to the end value, and we can specify number of data points if required. So so let us define this. Time is equal to lean space 1 to n det. Okay, so by default it goes as a column array, so we define it as a row array. Now you can see it is we did not specify the number of data points, so it has done that. So we need to define the now we have fractional data here, so that is obviously not serving our purpose, so we just define. So this is the time axis. So 1, 2, 3 up to 9840. Now we multiply it with the sampling interval. So that is dt is, we defined it, we have this sampling interval in our case as 200 samples per second. So dt is 0.005. So time axis is dt multiplied by time. So this is the total time axis. Now we can have a look at this is the plot of AX data. We can have the grid if we want. We can have labeling of the plot as well, and then manipulation of the font, etc. That is all possible. So those are bells and whistles which we can do it later on. And then again we can have multiple plots, all different windows. Oh, so it is overwriting or plotting on the same plot. So I can actually have figure 1, and that would be plot AX that you see here. Now I want to see the plot, second plot, to go on figure 2. So that gives, I just specify figure 2 and then give the plot command. So now I have, this is figure 2 AY, and figure 1 is here. So this is figure 1. So this is AX, this is AY, and similarly I can say figure 3 and then plot Z axis. So this is the figure number 3. So what we have done here, if we go back in the history, okay, it doesn't preserve that much. So so what we did was we have opened this file indicator, mapped this particular file to a uh, file handler, file handle, and then read it into this particular array. Uh, Total number of data are obviously 3 times the uh, 3 times the each sample data. So and that is the individual sample data, individual channel data. And then now the task is to extract individual file from individual component data from this composite data. Of course, we could have done it in a different way, but it's much easier to just read it from whatever is available. So we create 3 arrays AX of appropriate size, and that one column AY, again another array of and that size, AZ, another array of and that size, and then we try to extract it from different from this particular AX, AY, AZ into individual components. So we will do this in because total number of data for any channel is n dat. So this for loop runs from 1 to n dat. Now we need to figure out which component, which number should be picked up from the AX, AY, AZ, the composite data that we had. So this particular thing does that mapping for I running from 1 to n dat data. What should be the appropriate index level for X component of data? So that goes as I minus 1. So if I is 1, then it should get mapped to 1. If I is 2, then it should get mapped to 4. And that's how this happens. So in increment of 3, so I minus 1 multiplied by 3 plus 1, so that gives me the correct position in that composite data for X component. And similarly, I can go for y-axis data. So y-axis is next to the x-axis data, so increment goes as 2, and similarly for z-axis data, increment will be 3. And once I define this mapping, I just assign appropriate values. So AX, AY, Z, the JX index is mapped onto I, JY index is mapped onto AY, and JZ is mapped onto Z component. And that's all. And after that we have this is the linspace that we created. Normally default is it's a row vector. We want it to be a column vector, so we transpose it. So then the sampling interval is 0.005, that is by sampling rate of 200 samples per second, and then we convert that integer array of time into the absolute time units, multiplying it by dt, and these are the simple plots that we can generate. from this. So now comes so now we have complete data. Total acceleration, that is time ax, ay, az. So we have brought again the same all three components in the single array. So ACCN is the data file that you have, array, which first column is time, second column is x component of acceleration, and third column is y component of acceleration, and fourth column is the z component of acceleration. And now we can work with, similarly we can work with our data for LTA and STA ratio. So how to do that? We need to define, if you look at it, how do we first exercise is to find out what is the event start time. So for this you need STA by LTA ratio, right? So this is event start time as well as for event stop time. So now the way to do that is, we have this data, as you can see. So some part is, of course, there is a moving window which we define as long term window, and there is a window which we define as short time window. Right? So this is short time window, and this is what we call as long term, long time. Chalo. So what should be the total window length? That's a matter of debate. Whatever works, we should use whatever for the particular system of operations. We will try to have it as 200 samples to start with as long time window, and short time window we will have it 20 samples. So with 20 samples we have the resolution of about 0.01 second, and let's see if we can capture that information. So how to do that? ,20 samples is fine, but what do we how do we operate on this? So obviously we are looking at a sample lead of 220 samples. So this is total is a data length of about 220 samples. So we need to start, I mean, instead of our starting time that we had from 1, we need to start from maybe 221. And so our for loop maybe it will go up to end that, and then we try to find out what is the particular thing. So Sx is equal to, we define Ax I minus 22i, right? So these are the 20 samples that we assign for short-term record, and similarly for the x component, and similarly for the long-term average, we define Ax as I minus 220 to I minus 20. Or will it be 21? Right? And then we find there is a command STA will be that's the average, short term average. So sum of squares of Sx, we could have taken the absolute values as well. So the idea is to get rid of the sign. So either we run the sum and we compute the sum of absolute values, or we just compute the sum of squares of these all data that we have. And this is the length of the array. So number of data points that we have here. And similarly, LTA would be equal to sum of squares Lx divided by, again, length of Lx. So now this STA by LTA that we compute, that will correspond to this value of I, this particular instant of I. So we define, before that we can define STA LTA ratio is equal to, again define an array of and dat one, and then this ratio STA LTA ratio I is equal to STA by LTA. and that's what it will have, and we just stop this array here, for loop here, and then we'll see what how the plot looks like of STA LTA ratio. So let us work out this, how it goes in the octave. So we need to define two arrays. So let's say, let me just see what is the length it comes out to. Sx is equal to Ax. Okay, so there is an offset of 1, so 21 okay. Okay, fine. So it will be 19, and from here it will be I minus I minus 220 to I minus 90. Is that? doesn't matter, चलो 21 का ले लेते हैं. So we define this STA-LTA ratio as an array of n dat number of points, and uh, one column we can actually do it 3 columns, no problem, for all 3 components, and then see so for I is equal to 221 to n dat. So we have Sx as Ax I minus 20 to I, Lx as Ax I minus 220 to I, हाँ टिमरी जी, नमस्कार नमस्कार.
सर 2-3 इन्वेस्टमेंट थे सर.
हाँ ठीक है, ऑफिस भेज दीजिए.
ठीक है.
ठीक. So this will be Sx to I, fine, and similarly we define short term for Sy as Ay I minus 220 to I minus 20 to I, and Ly as Ay I minus 220 to I. No, that is not right. What happened? Was there some message here? SZ, and similarly for LZ. Now we can define STA versus LTA. So STA, sum of square of this short term array divided by length of array, and LTA as sum of square of long term array. So STAX is equal to sum square SX divided by length of SX. LTAX is equal to sum of square LX divided by length of LX. Similarly, we define for Y, we define for short term and long term for Y, and then Z, LTAZ, and then STAZ. So now we have all these ratios available, and we just save it in the STA LTA ratio. I is equal to STAX by LTAX. So that's the first column that contains the X component. Second column will contain the Y component. And third column will contain the Z component ratio. And that's the end of it. Now we can plot time, STA, LTA ratio, what happened? What is this STA LTA ratio? Yeah, fine. Time, so Namaskar. So this is the plot of STA LTA ratio. We will look at it in a greater detail, and I guess just a minute, let me. So as you can see, so figure 1, and so this is of course the time, and we can define the grid.
Hello.
Hello, Jia.
Hello. Hello.
हाँ जिया सर.
Hello.
Oh, okay. हाँ, hello. Yep.
Yeah. Actually, now it is okay. Previously, no sound was coming.
हाँ, वो बीच में कोई आ गया था कागज साइन कराने, तब म्यूट कर दिया था.
Okay. Okay. No,
So
no issue.
ठीक है. So this is what it is. So I just advise, suggest that you can play around with this data, different sets of data, and work out this LTA, STA, LTA ratio, and find out what is the trigger hole value. Right. So this will be around. We can zoom the data here in this range, and that will provide us the information.
To find out this value from our data,
Yeah,
from different sets of data.
sure. And this is of course the constant line that 45-degree slope, the that needs to be plot syntax has to be corrected. So that we will figure out. You can figure out how to plot individual component, and triggering is usually done by the vertical component. Vertical components usually arrive before the horizontal components. So you might see some difference in STA LTA ratio in different components. So you might get a earlier trigger from the vertical component. So just have a look at it, and we will return to that, and in the meantime I will also work on data and have a more proper sequence of operations and demonstration ready. And once we do that, then we will extract that particular stretch of data, which will be the earthquake data, and for that we will then implement the baseline correction and subsequent processing.
So, won't it be better that if we work it out parallelly on the same set of data, like
Yes,
the
yes,
on, we will
that's perfectly
give it a
fine.
try
That will be
here.
better. Everybody works on the same set of data so that we can uh,
We can validate the
we
results.
can compare what is happening and what is going on. So
Okay, sir. Huh.
so maybe you can share the data, any data file, and all of us will work on the same data.
Okay, sir. So we will identify a few events, and then actually I have already done that. So I will finalize it, and maybe in a day or so I will share it with you,
Yeah,
so
sure.
that we on the both ends we can work on the same set together.
Sure. That's great. Yeah.
Okay, sir.
So we'll close the session here. It's very long today. So,
Yeah.
so recording is going to be massive size. Okay, it will take
Yes.
some time to upload. Fine.
Yeah.
Okay. Thanks.
Yeah.
We'll meet
Yeah.
next
Sir,
week.
sir, I have one question.
Ji हाँ.
Hello. whatever we are working, this is very good, and we are getting a lot of things from all this, whatever you are providing data and the software details, everything. Uh, Finally, actually, there is one thing which I always think that we should do something for that also.
हाँ. आपकी आवाज़ नहीं आ रही.
Sir, your voice is not audible. Sir, you are not audible. Kapil sir, your voice is not audible.